Okay, so in this video, I'm going to talk about trade in a pure exchange economy. So these agents, there's no price, exchange the goods with the initial endowment that they begin with. So where should they end up? So if they begin with the initial endowments, well then trade will occur and the final allocation will be X if and only if, one, X is feasible, obviously. I mean, when they trade, they should end up with a feasible allocation. Two, the trade, that's an assumption, all right? So we assume that trade will continue until they exhaust all the potential mutual gains from trade. So X is therefore Pareto efficient. All right. And then finally, the utility of X should be greater than, for example, agent A getting everything and B getting nothing, or agent B getting nothing, agent A getting everything. These are all Pareto efficient allocations under some, utility, many utility functions. But can they end up trading there? No. The utility for agent A under X should be greater than or equal to utility of agent A under his initial endowment, WA, and the same must be true for agent B. All right. I mean, both agents should be preferring the trade. So the trade is trade is voluntary. All right. So this is what it means. Trade is voluntary. No one can force you to trade. So therefore, if you trade, you shouldn't end up giving everything you have to the other party, assuming that you actually enjoy these goods. The trading outcome is Pareto efficient means, the trade is efficient, all right? And the trade is feasible, all right? I think there's no point of writing that. So that's it. So the trade will occur and the trading outcome is going to be feasible, it's going to be efficient, and it's voluntary, it's preferable, all right? So here, for example, graphically, what it means, if I have initial endowments, I can draw the Edgeworth box, agent A here, agent B here, and let's say the initial endowment is here. So assuming that initial endowment is not Pareto optimal, probably agent A's indifference curve is passing through the initial endowment is going to be like this. Agent B's utility is going to be like this. And so there's going to be a contract curve. So therefore, all the allocations here actually satisfy those three properties. They all are feasible, they all are Pareto efficient, and they all giving both agent A and B higher utility. So by the way, one of them must strict. So we don't have that here. So therefore, all these, there are infinitely many such possibilities. All of those are potential trade outcomes when there is no price. Okay? Well, if, however, suppose that the initial endowment is on the contract curve, all right? So that's the initial endowment. It means the agent A's utility, agent B's utility, and agent A's utility, the indifference curves, are tangent to each other at that point. So that means there's only one point which satisfies those three properties, which is the initial endowment itself. And that means if the initial endowment is Pareto efficient, the agents actually shouldn't trade because there is no other feasible allocation and Pareto efficient allocation, which is going to make both agents happier. There's no such allocation, and hence the agents should not trade at all. All right. So mathematically, therefore, how can you calculate the set of Pareto? The set of potential trade outcomes? Well, simple. One, calculate the contract curve. All right. So write XA as a function of write YA as a function of XA, and then two, use condition 3 above to come up with some limits on XA and YA. All right. So calculate the contract curve, i.e. write YA as a function of XA, and then come up with some limits on XA and YA. So that's it. So we can do a numerical example. So let's do one simple numerical example. All right. So here is sort of similar to the examples we already solved. So the WA is, let's say, 2, 1. WB is 2, 1. And the utility of agent A and B are x times y. All right, or square root of x times y. It doesn't matter. So what we know, I'm going to skip the margin rate of substitution business. YA divided by XA equals to YB divided by XB. This is the contract curve, if you remember. So if you use the feasibility, XA plus XB equals to 4, and then YA plus YB equals to the total good Y, which is 2. So therefore, write 4 minus XA rather than XB, and write 2 minus YA rather than YB. So therefore, YA divided by XA equals to YB, which is 2 minus YA divided by 4 minus XA. So bear with me, do the cross product, which means 4YA minus YAXA equals to 2XA minus XAYA. I hope you can see that, yeah. So what do I have? XAYA is cancelled out. So I have YA equals 1 over 2XA. So this is the contract curve, all right? So let me clean up this part. So what I have is then use the condition 3. So what is condition 3? Condition 3 is the following. UA XY has to be greater than or equal to UAWA, which is agent A's utility is just 2 times 1, which is 2. All right. So what is agent A's utility, which is XA times YA greater than or equal to 2? Well, and the same for agent B, right? XB times YB must be greater than or equal to 2. So what I have is the following. Remember, YA has to be equal to 1 over 2XA. So this inequality, therefore, becomes 1/2 XA times XA. So whenever I see YA, I just plug 1 over 2XA greater than or equal to 2, or put differently, XA square greater than or equal to 4, or XA greater than or equal to 2. So the agent A should be consuming more than 2. And then, oh, by the way, this is, well, okay, I'll come to that. And then symmetrically, we have to come up with, if XA is greater than 2, that means YA, which is equal to 1 over 2XA, has to be equal to greater than 1. All right? Well, what about the B's, though? Well, I would like to write everything as a function of XA and YA. So whenever you see XB, just write 4 minus XA. And whenever you see YB, just write 2 minus YA. Has to be greater than or equal to 2. And then once again, whenever you see YA, just plug 2 minus 1 over 2XA times 4 minus XA greater than or equal to 2. So that's going to be a bit more complicated. So let's see what it's look like. So this is 8 minus 2XA minus 2XA plus 1 over 2xa squared. I wish one of this was positive, the other was negative, but yeah, there's no hope. So greater than or equal to 2. So basically, what I have is 1 over 2xa squared minus 4xa plus 6 greater than or equal to 0. So xa not only should be greater than or equal to 2, but it should also satisfy this. All right. For example, can xa, well, yeah, I think, so if xa is 2, for example, so this is going to be 4 divided by 2 minus 8. Yeah, this is going to be 0. So if xa is, for example, 3, all right, so if xa is 3, so this is going to be, or 4, so if xa is 4, for example, so this is going to be 8 minus 16 plus 6. Oh, this is going to be negative. So therefore, this is going to give me some upper bound for xa. So in conclusion, the trade outcomes are such that xa greater than or equal to 2, 1/2 xa squared minus 4xa plus 6 greater than or equal to 0, and then ya greater than or equal to 1. Well, in fact, better than that, ya is equal to 1 over 2xa. All right? So any xa and ya satisfying these 3 conditions are potential trade outcomes. So basically what we did is, let's draw the Edgeworth box. So this is 4 by 2. So this is 4 by 2. All right, and the initial endowment is 2, 1. So 2, 1, the midpoint. But apparently, is the midpoint pretty efficient, by the way? Oh yeah, it is. Well, yeah, this is my guess. Anyway, by the way. So ya is equal to 1 over 2xa, right? So if you look at the initial endowment, it does satisfy the contract curve. I mean, it is on the contract curve because xa is 2, therefore ya is 1. Yes. So therefore, this is exactly so this is what the contract curve is, and the initial endowment is on the contract curve. So therefore, it means there is no xa other than 2, 1, which satisfy this property. So it must be this. So therefore, the trade outcomes are such that W is the only trade outcome. All right? Because, I mean, you can check, there's going to be no other XAs. All right? I hope that was clear.